Welcome, dear students. We are going to study shift registers, and we know that we are having four types of shift registers depending upon the input given and output taken from the shift registers. And we have already studied two types of shift registers, namely SISO, serial in, serial out. Here you are applying input serially, that is bit by bit, and you are taking output serially, that is bit by bit. And we have already studied SIPO, serial in, parallel out, in which the input is given bit by bit and hence serial in, and outputs are taken simultaneously, therefore parallel out. Now today we shall discuss about PISO and PIPO, parallel in, serial out, and parallel in, parallel out. First we shall discuss about parallel in and parallel out to shift 4 binary bit. So parallel in, parallel out, shift register. Here the input is parallel, output is also parallel. That means you have to apply input simultaneously to all the flip-flops, and you have to take the output simultaneously from all the flip-flop. Both are simultaneous. At a single step you have to apply the input, at a single step you have to take the output. That is parallel in and parallel out. I will write 4-bit shift register of parallel in, parallel out. You know that each bit requires one D flip flop. Therefore, to shift 4 bit, you need 4 D type flip flop. First, you write the D flip flops. So, in order to shift 4 bits, write 4 D flip flops. 1, 2, third flip flop, D type flip flop, fourth D type flip flop. You know that D is the input. I will consider this as a flip flop 3. D3 is the input and Q3 is the output. Here D2 is the input and Q2 is the output for the second flip flop. Flip flop 2. For the flip flop number 1, D1 is the input and Q1 is the output. For the flip flop 0, D0 is the input and Q0 is the output. And we know that the action of D flip flop, whatever the value presented to D goes to the output Q3 when clock pulse is present. Therefore, apply clock pulse simultaneously to all the flip flop. Since you are applying clock pulse simultaneously to all the flip flop, connect the clock pulses of all the D type flip flop to a single clock pulse. This is our input clock pulse, and I will represent the rising edge. So when this rising edge enters, whatever may be the value at D3 is shifted to Q3, and whatever the value at D2 is shifted to Q2. The value at D1 is shifted to Q1. The value at D0 is shifted to Q0 when the clock pulse enters. When the first clock pulse enters here, since all are connected to a single clock pulse, the same clock pulse enters to all the flip-flops simultaneously. Here, parallel in, there you have to apply input in a parallel manner. Therefore, you have to apply input to all the flip-flop at a time only. Therefore, I will apply input D3. I will apply input D2 here. I will apply input D1 here, and I will apply input D0 here. I will explain this with an example. Let the input be 1011. This 1011 is applied to all the flip-flop simultaneously. Now, parallel out means output has to be taken simultaneously. Therefore, take the output from Q3, take the output from Q2, take the output from Q1, take the output from Q0. So this is a simple block diagram of 4-bit parallel in, parallel out shift register. I will explain this with an example. Let a binary bit 1011 is applied simultaneously to all the flip-flop. Therefore, the input is parallel. When the first clock pulse enters, it enters to all the flip-flop. And we know that when the clock pulse enters, whatever may be the value at D3 shifted to Q3. So in this flip-flop, 1 is the value at D3, it is shifted to Q3. So Q3 is 1. For this flip-flop, 0 is the value D2, it is shifted out. Therefore, this Q2 is 0. Similarly, 1 is the value at D1. When clock pulse enters, it is shifted to Q1, that is 1. Here 1 is the input value for this flip-flop. When clock pulse enters, this is shifted to Q0. Therefore, Q0 goes to 1. Now you are taking directly the output from all the flip-flop. That is Q3 is 1, Q2 is 0, Q1 is 1, Q0 is 1. 1011 is the output. The input applied is 1011. Therefore, you are applying input simultaneously, that is parallel input, and you are taking output simultaneously, that is parallel output. How many pulses required to get all the 4-bit? Only one clock pulse is required here, because 1010, 1011 are the inputs applied. During first clock pulse itself, it is applied to all the flip-flop, and the input is transferred to the output. Output of the flip-flops are taken directly 1011. Therefore, only one clock pulse is needed. This is the much great advantages of PIPO, parallel in, parallel out. It requires only one clock pulses for any number of shifting. The n-bit shift requires single clock pulse. 4-bit requires single clock pulses. 8-bit requires single clock pulses. Generally, n-bit requires single clock pulse, because all the n bits are applied at a time and all the bits are taken at a time. Simultaneously, we are taking output. Therefore, a single clock pulse is needed to get all the output, because all the clock inputs are connected to a single clock pulse. This is parallel in, parallel out. This is the only advantage. It requires a single clock pulse. Now let us study other type of flip-flop, the last flip-flop, PISO, parallel in and serial out. In this parallel in, serial out, you are applying input parallelly, that is, you are applying input simultaneously. When you apply the input, all the input must appear as the input for all the D flip-flop, because it is parallel in. Therefore, the input applied must appear simultaneously to all the flip-flops. But you have to take the output bit by bit, one by one, because serial out. So serial means taking the output bit by bit. If one clock pulse enters, you will get 1 bit. When the next clock pulse enters, you get second bit. When the third clock pulse enters, you will get third bit. When the fourth clock pulse enters, you will get fourth bit. But inputs are applied simultaneously, the parallel in and serial out. So to get a single bit out, you need one clock pulses. So this is parallel in, serial out. So in parallel in, serial out, all the inputs are applied simultaneously to all the flip-flops, whereas output is taken bit by bit. Now you will study with block diagram. You just observe how I will write the block diagram of parallel in serial out. We are discussing about 4-bit shift register. So we are shifting only 4-bit, but the shift register is parallel in serial out. So you have to apply all the 4 bits simultaneously as the input, and you have to take the output bit by bit, that is parallel in serial out. Since we are shifting 4-bit, you require 4D type of flip-flop. First you write all the 4D flip-flop. This is I will write here. I will show how to write. Write 1D flip-flop, flip-flop 3, write another D type flip-flop, flip-flop 2, write one more D flip-flop, flip-flop 1, write the fourth flip-flop represented as flip-flop 0. D3 is the input, D2 is the input, D1 is the input of this, and D0 is the input of this. Q3 is the output, Q2 is the output of second, Q1 is the output of third, and Q0 is the output of the last. Now you are applying input simultaneously, but output should be taken bit by bit. Therefore, you have to use another sequential logic circuit between the two flip-flop. So in order to apply input simultaneously and to take the output serially between the two flip-flops, you need some sequential logic circuit. Therefore, between these two, write that sequential logic circuit. I will write that sequential logic circuit here. 2 AND gate. This is AND gate, and the output of AND gate is taken as the input for OR gate, and this is the output of OR gate. Again write here 2 AND gate, output of the 2 AND gate are connected to 2 inputs OR gate. One more sequential logic circuit, AND gate, output of these 2 AND gates are taken as inputs for this OR gate. Now apply the output of this OR gate to D2. Apply the output of this OR gate to D1. Apply the output of this to D0. Okay. Then take, this is 2-pin AND gate. This is 2-pin AND gate. 2 inputs AND gate. So one of the input is connected to Q3. Connect this to Q3. Connect this input to Q2. Connect this input to Q1. You just mark that how I am writing. Output of OR gate is connected to the input of D type flip-flop, and one input of the AND gate is connected to output of the previous D flip-flop. Now I will consider two lines. One is complementary line, another is uncomplimentary line. Okay, this is uncomplementary line. This is a complementary line because I have connect this line to this through a NOT gate. If this line is logically 1, it is logically 0. If this line is logically 0, because of NOT gate, this line becomes logically 1. So consider these two lines. Now apply the input to all the flip-flops. Okay, I will apply the input to D3 and I will apply another input to this manner. I will apply another input to this AND gate and I will apply the last input to this one and call this as input B3, input B2, input B1, input B0. That is 4-bit B0, B1, B2, B3. These 4-bit must be applied to all the 4 flip-flop simultaneously. Therefore, it is parallel in. But the output from the flip-flop Q0 is the output of the last flip-flop. The output from the flip-flop, that is Q0, is taken bit by bit. Therefore, it is serial out. Now, I will connect this second input of this NAND gate to complementary line. Okay, and this two line uncomplementary line. One inputs are connected to complementary lines, another inputs are connected to uncomplementary line. And I will mention this line as load bar shift S bar because this is a line we can load this value B3, B2, B1, B0 to this all flip-flops. Therefore, this line is called load. It is also shift line because using this line you can get the output one by one. That is, the input is applied simultaneously. For that you have to use this line as L is equal to 1. That is load input. When this is 1, this becomes 0. In order to shift the output, make this line as 0. When this becomes 0, this output is 1. Therefore, I will call this line as load input bar shift bar input because when this is L is equal to 1, S bar becomes 0. When L becomes 0, S bar becomes 1. These two are the lines. This is L line, this is S bar line. Therefore, this is the input line of L by S bar, load by shift bar. If you make this one, it acts as a load. All the inputs are loaded simultaneously. If you make this as 0, then S bar goes to 1. It acts as a shift. Then the bit is shifted out one by one. Now let us see how all the inputs are applied simultaneously with an example. Let B3, B2, B1, B0 are the bit itself. Now when this load line is equal to 1, during the load operation, you have to load all these bits simultaneously to this. During load operations, you have to make this 1. So when load is equal to 1, because of this complementary, this becomes 0. So see, this is 1 and this line is 1. This line is 1. Here B3 is applied to this. Therefore, D3 is equal to B3. Here B2 is applied. This is B2. Here B1 is applied. This is B1. Here B0 is applied. This is B0. This AND gate is connected to NOT gate. That is, if this is 1, this is 0. Therefore, this is 0. Again, this is 0. This line is 0. And we know that among number of inputs of NAND gate, if any one input is 0, output is 0, because 0 into 1 is 0. Since this is 0, output of this AND gate is 0. So 1 into B2, output of this AND gate is B2. 0, if this is 0, output should be 0. So 1 into B1, output of this AND gate is B1. 0 into anything is 0, AND gate output is 0. 1 into B0, output of this AND gate is B0. This is OR gate. So output is sum of the two inputs in OR gate. Therefore, the output of this OR gate is 0 plus B2 is B2. Output of this OR gate is 0 plus B1 is B1. Output of this OR gate is 0 plus B0, that is B0. And of course, B3 is applied directly. Now you see that when L is made 1, what are the inputs of all the 4 D flip-flop? For the first, it is B3. For the second, it is B2. For the third, it is B1. And for this last, it is B0. So B0, B1, B2, B3 are applied to all the inputs of the flip-flop simultaneously. Therefore, this shows that the input is parallel. Now we have to shift it one by one. Let us see how it is shifted one by one. Now, in order to shift, you make this line 0. When this is 0, it becomes 1. Now this line becomes 1. This line becomes 1. This line becomes 1. And this line becomes 0. So this line becomes 0. And this line becomes 0. This line becomes 0. We know 0 into B2 is 0 itself. Output of this AND gate is 0. 0 into B1 is 0. Therefore, this is 0. 0 into B0 is 0. This is 0. So, during shifting process, output of these AND gates is 0, 0, 0. Now, apply clock pulses simultaneously to all the flip-flop. During shifting process, you need clock pulses. Therefore, apply clock pulses to all the 4 type of D flip-flop simultaneously. Simultaneously you apply. This is a clock pulse. This is input clock pulse. Input clock pulse. We know that when clock pulse enters to the flip-flop, D-type flip-flop, whatever the value present at D3 shifted to Q3. Now, the value present at D3 is B3. When the clock pulse enters, this B3 shifted to Q3. Therefore, output of Q3 now becomes B3. Now, D2 is the input. When clock pulse enters, it is shifted out. Therefore, output of Q2 is B2. B1 is the input applied at D1. Okay, P1 is the input applied to D1. When clock pulse enters, input at D1, that is B1 is shifted to Q1. Therefore, Q1 is B1. And similarly, the input B0 at D0 is shifted to Q0. Therefore, Q0 output is B0. Thus, output is our Q0. You get first bit B0. When the second clock pulse enters, this B3 shifted to here because this acts as a input for this. During the second clock pulse, this B3 shifted here. This B2 is shifted here. This B1 is shifted out. So you get 2 bits for 2 clock pulses. During third clock pulses, this B3 shifted here. This B2 is shifted here. You get 3 bits out. During the fourth clock pulse, this B3 is shifted. Sorry. Yes, this is B2. Previous B2. B3 shifted here. Thus, you have taken all the 4 bit out, but one by one. When one clock pulse enters, you get B0. When the next second clock pulse enters, you get B1. When the next clock pulse enters, you get B2. When the fourth clock pulse enters, you get last digit B3. That means you are taking the output bit by bit. Therefore, this is serial out. So when this load line is made 1, all the inputs are applied simultaneously. When the load line is made 0, shift line becomes 1. In that case, during the first clock pulse, 1 bit is transferred. During the second clock pulse, second bit is transferred to the output. During the third bit is transferred. During the fourth clock pulse, fourth bit is transferred to the output. Therefore, you need only 4 clock pulses to get all the 4 bit out. In general, if n is the number of clock pulses or if n is the number of bits to be transferred, then the number of clock pulses required is n itself. For 4 pulses, you need 4 clock pulses. Therefore, for n clock pulses, you require, for transmission of n bits, you require n clock pulses. For 1 clock pulses, let the small t is the time taken. For n clock pulses, time taken is nt. Therefore, time taken to shift n number of clock pulses is given by t equals n into t, where small t is time required to shift only 1 clock pulse. This is how parallel in serial out works. Thank you.